Okay. All right, everybody. Welcome to this year's edition of DevSecOps Live. DevSecOps Live is a live webinar brought to you by Practical DevSecOps. My name is Modern. I'm your host, and I also happen to be the presenter for today's content that is in different ways. There's many different ways to manage secrets in Kubernetes. I'm a principal consultant at Practical DevSecOps. Practical DevSecOps excels in consulting and training, providing a lot of training curriculum and certifications. Check out our website. And what I'm going to be presenting is also a part of our course, but we thought it's best to present this content individually because secret management in Kubernetes, it's not very straightforward and it can be confusing. And it can also be, it can be easy to get started with, but to secure those secrets might require a coordinated approach from a design perspective. Okay, so this webinar is being recorded. It will be available in our YouTube channel. The links to the YouTube channel, if you don't know already, that would be www.youtube.com/practicaldevsecops, one word. But other than that, other links and upcoming webinars will be available at our YouTube channel. Okay, so I'm gonna get started with sharing my screen. And that's the lab that I'm going to be presenting afterwards. And here's the presentation. So, secret, without further ado, let's get started right away. If you have questions, put them in the Q&A section. That's something that we can look at afterwards. But then we're going to first start looking at Kubernetes itself and where secret leakage can happen in Kubernetes. So you are required to have some level of knowledge within Kubernetes. That is where secrets are stored. What are the different components that are available within the Kubernetes cluster and where container runtime is actually present in the architecture. But if not, there are a few slides that will cover them along the way. So number one, people create Kubernetes resources using what's called a manifest file. And these manifest files can also contain secrets because in the perspective of Kubernetes, secrets is a special type of Kubernetes object. Just like how you have a cluster, which is a Kubernetes object, you have a node, which is a Kubernetes object, you have a pod, which is a Kubernetes object, which runs your workloads ultimately. You also have a secret, which is a Kubernetes object. And if you want to create secrets within Kubernetes clusters, you would want to preferably create them using manifest files. And when you create them in source code, you'll have to commit them to source code version control system. And that's the place where secret leakage can happen within Kubernetes. And when people create a cluster to join nodes and for other purposes, they might use tools like Ansible or other infrastructure as code tools. Those tools can also contain secrets. So your manifest files in Kubernetes can contain secrets, and also your configuration files that you use to orchestrate your cluster, that can also contain secrets. And they go to the version control system where secrets can get leaked. And then inside your container workloads, you're going to have your executables. And these executables and binaries can contain secrets inside them. That's also a place where secrets can get leaked. And then your container layers, the many number of layers that make up your container's file system, they also can contain secrets. Why? Because someone may have added them accidentally using the copy or add command when they were creating a Docker file. And then secrets are stored in the etcd cluster. It's a part of Kubernetes cluster component. And if someone has direct access to the etcd data store, they might have access to the secrets directly. Okay, so storing secrets in plain text, storing secrets in container images, and container image layers, and then having direct access to the database itself. These are some ways, and cluster configs, these are some ways secrets can get leaked, right? But first, we're going to review them one by one. And first, we're going to look at the Kubernetes secret object itself, what it is, how to create one, how to access one, how to edit one, and how to actually get into the place where it actually gets stored in the back end, and review how our actual secret object looks like. So Kubernetes secret object is an object that is meant to store secrets. It's good for one reason, that if you have secrets in multiple places, it helps you create all those secrets in one single place inside the Kubernetes cluster itself. That's what it's good for. And it's stored as a key value pair, and it's stored in a base 64 encoded format, and it is not encrypted by default. It's something that you will have to do. It's something that you will have to encrypt by default at storage. Okay, and just like any other Kubernetes object, you would also want to have role-based access control to access what type of Kubernetes user can access a particular secret present in a particular namespace or in all namespaces. Okay, so Kubernetes secret is a secret object. It's a key value pair within the Kubernetes cluster, not encrypted by default. It's base 64 encoded. Helps you consolidate all your application secrets or infrastructure secrets in one single place, and that is the Kubernetes secret object. Now, how do you create a Kubernetes secret object? Remember, on the few minutes ago, I said you can create them using manifest files. But there are also other ways to create Kubernetes secret object. That's by using the kubectl command. And there are different types of secrets available within Kubernetes. All of them are base 64 encoded and not encrypted. So here's a command that says kubectl, create a secret object, call the secret object my-secret, and make sure this is a generic type of secret. A generic type of secret uses simple key value pairs within itself. And you see there, there's a username called my username, and there's a password called my password. And we're creating the secret using literal strings. And that's why we have the -- from literal object. You can also create the secret from files, in which case you would use -- from file instead of using -- from -literal. So there are different ways to create the secret, and this type of secret is called generic secret. There are specific types available for public-private keys. That's the type of secret you can create within Kubernetes. There's a specific type of secret to access a Docker or a container registry, to authenticate yourself to the registry. So that's another type of registry credential secret you can create. But this secret here is a very simple secret called generic. That's the type of secret. But once this is created, you can get the secret using the kubectl command. And once you get the secret, this is the output that you would see, that this secret is called a the kind of the Kubernetes object is called secret, and the username and password is actually there, not in plain text, but base 64 encoded. And notice at the bottom, it says the type is opaque. So opaque is the actual type of Kubernetes object. And when you use the kubectl create secret command, you would refer to the opaque type of secret as the generic secret. Okay, so even though in the kubectl command you say generic, the actual type of secret that gets created behind the scenes is opaque. But if you were creating the same secret using a manifest file, you wouldn't use the type as generic. You would use the type as opaque. And that's what we're going to see next, how to create secret with manifest files. Okay, so here we have we're creating, first we need our strings in base64 format, and that's what we're doing there. We're base64 encoding my dash username, or base64 encoding my dash password. And then we will create a manifest file. And then we will do kubectl apply command on that manifest file, which will lead to the creation of this particular object. What's the name of the secret here? Can anyone spot the name of the secret there? If you look at the metadata section, there's a name that says my-secret2. So that's the name of the secret. And this secret object has two data in it. One is the username, another one is the password with their base64 encoded values. Let's see how to query these secrets from the Kubernetes secret object. We've seen this in a previous step. You could do that with the kubectl command, kubectl get secrets. But if you do kubectl get secrets in the YAML format, it will give you the YAML of the complete file. You can also query particular fields within that secret object and directly base64 decode it using the base64-d command. That's also possible. Okay, so we've seen how to create secrets from literal, right? So how do you create secret from a particular file? Well, here's a way. So we're doing kubectl create a generic type of secret again. The name of the secret is my-ssh-secret-keys, and we're creating this from a file. Okay, once you do that, and once you create that secret, when you get the secret back, there's your secret. The SSH private key was read from that file, and it was placed inside that SSH private key for you, and the SSH public key was also read from that file, and there's that value. Okay, and what do we have next? So we've seen how these secrets behave. We haven't seen a demonstration of it. I'm going to quickly jump into my lab environment here, and I'm going to show you how all this works. So I'm going to quickly jump into step 1 here, create a secret. Okay, before that, we're creating a namespace here called lab. And I'm assuming that we're going to create this particular secret inside that namespace. Okay, so here's a kubectl create command there. If you don't know what this command, I might have made a mistake there. Let me do a Control-C on this. Let me copy and paste this again. Okay, so what are we doing with this command here? We created a secret object. There's also some little explanations built into this platform here. We can use that for our advantage. So we're using the kubectl create command to create a generic secret named mySecret inside a namespace named lab. We're creating that from literal, right? So after we do that, what are we doing? We're then getting that secret, right? Let's get that secret there. And you see, when we get that secret, so that's the secret that we created. And there is the my key value. If you're curious what this my key value is, you can actually echo this and send it to the base64-d command that will decode that value for you. And that is the my value. So that's the secret that we created. This is fine because when we create a secret, when you want to retrieve it from our secret store, we want our secrets to be accessible in plain text so we can contact our third-party systems and use that secret meaningfully for authentication purposes. So we need the secret in plain text anyway. And that's what the kubectl get secret method was giving us, for the plain text secret. So we've actually also base64 decoded it. But what I want to show you here is I want to get inside. This is a single node cluster that we have. And within this cluster, the etcd data store is the store that ultimately stores your secrets in the file system. And this is a single node cluster, and we have an etcd pod that is responsible for creating our secrets and other Kubernetes objects. So what we're going to do is we're going to get inside the etcd pod, right? We're going to get inside the etcd pod. We haven't gotten inside yet, right? We haven't gotten inside yet. We're grabbing a few details so we can get inside the etcd pod. What is the details that we need? Okay, we need the private key files and the other things. Okay, so let's execute that command. And so what we did here, right? This is a pretty long command, by the way, and I can try and break it down in my text editor here. So we're running a command inside the etcd pod, and this is the command that we're running, right? We're running a command called etcdctl. We're passing some server certificates and key to authenticate against them, right? And then finally, we're getting this particular object on the etcd data store. So if I cut all this extra authentication steps and exporting that variable, we're getting inside the etcd pod, then executing a command that will read the value of my first secret from the etcd data store. And that's what we did. So we have the value here called my value, right? This is by default, right? If you ever have a Kubernetes cluster and you create a Kubernetes secret object, this is how the secret store is going to behave. You can also get inside the pod and try and read the database itself manually because it's stored in this particular location. We're not going to do that because we have other things to review for the moment. So we've seen how secrets are stored. But how do secrets actually can be encrypted, right? So if we look at the flow pictorially of what we did, right? So there's the etcd data store, which stored the secret in an unencrypted base64 encoded fashion. This is the demonstration that we saw inside our single node Kubernetes cluster, right? We created a secret, got stored in the etcd data store, unencrypted, base64 encoded, right? In order to encrypt these secrets, you have to create a special kind of manifest called encryption configuration. And you have to specifically instruct the Kubernetes API server to encrypt secrets. There are also other types of object you can encrypt if you would like. But in this example, we're only encrypting secrets. And when you want to encrypt something, you have to figure out what encryption algorithm you want. And when you figure out an algorithm, you have to have an encryption key. So those are the things that are present in the encryption configuration file. Okay, so you will create this file within your Kubernetes cluster. You would point your Kubernetes cluster's API server to the location of this encryption configuration file, right? So in order to do this, we'll have to do a couple of things. First, we'll have to go to the Kubernetes API server, create this encryption configuration, and then supply a special command line to the Kubernetes API server pointing to the encryption configuration location. And from then on, every time you create a secret, every time you create a secret, that secret's going to be encrypted and base64 encoded. Okay? So that secret's going to be encrypted and base64 encoded. So how can secrets be decrypted in this fashion? Well, if you just use the kubectl get command, the secrets will be automatically decrypted for you transparently, right? Just like how you have the file vault software in Mac for your hard drive or the BitLocker for your Windows computer. Well, the moment you enter your decryption password, the file system is being transparently decrypted to you. The same functionality here, right? Also in Oracle database or Microsoft SQL Server databases, if you enable encryption at the database level, they get decrypted for you when you want to access the data legitimately through SQL commands. So similarly here, through Kubernetes command line or the Kubernetes API, when you want to access the secret, they get decrypted for you, right? But where does the secret get encrypted and stored? Actually, well, that happens in the etcd data store. So the encryption configuration is actually trying to prevent if an attacker gets a hold of your etcd data store and they have it offline in another computer and they try to access the secrets within the etcd data store, well, they can't access plain text secrets because it's encrypted, right? So that's what encryption configuration is trying to protect you against, right? So we're going to see this demonstration. And to do this, I'm going to create a random number that's present in this variable called mySecret. So what's our random number? Okay. So that's our random number. So this is going to be the encryption and the decryption key that we're going to provide to our API server. Okay, so let's get into the etc Kubernetes location where there are a number of files with respect to the Kubernetes server itself. And then we'll create a directory called EMC, which implies encryption. And then this is our encryption configuration file that we're going to create, right? So if I look at EMC-configuration, okay, cat EMC-EMC- what am I missing? Okay, I'll have to type it out. Configuration.yaml. Okay, else minus AL. Did I create that file? Okay, let's get inside EMC. And there is our encryption configuration file. Okay, I must have specified the path incorrectly. Okay, so here is our encryption configuration file. And just like how we saw on the slides, we're saying we want to encrypt the secrets that get stored in the etcd data store using the AES algorithm. CBC stands for cipher block chaining, which is a specific mode of chaining available in AES. And then we're saying this is the secret key that you should use for encryption and decryption. So this is one, right? We have done this. We have created this. All that is left is pointing our API server to this particular file, right? Because this is a single node cluster and the API server here is also running as a pod, right? And I'll show this to you, kube-system namespace. So there you have the API server also running as a pod. We have to mount this directory as a volume inside that pod first. And then we'll have to supply this location to the etcd, to the API server to perform the encryption of secrets. Okay, and those are the steps that we're going to do now. Before modifying the API server configuration, it's good to take backup because if we make mistakes, then things might go wrong. So I'm going to edit the API server's configuration. What's the first thing that we're going to edit? Okay, the first thing is we supply the location of the encryption provider. And I have to come all the way down here. And that's where I want to add that setting. Okay, great. We've done that. And then under volume mounts, so because this is a pod, it also has data storage using volume mounts. Let me go down and figure out where volume mounts are. So there are volume mounts. I have to come down here. I have to add this particular volume mount to make that file, to make that encryption configuration file accessible inside this API server pod. Okay. And then down below I go. After the volume mount, I add the volume itself. Okay, so here's the volume. Now this is a host path volume, which means it shares the current host's path. That's why it's called a host path volume. I guess that should be it. And I'm going to do Control O on Nano, save this file, Control X to exit. The moment I save and exit, when I try to get pods, I'm actually not going to get any pods because the API server should be restarting right now. Any change to the API server's configuration triggers a restart of the API server. It's restarting right now. It hasn't come back yet. Should come back in about 30 to 40 seconds in our lab environment. And if it hasn't come back in 30 or 40 seconds, then it means we might have made a mistake in editing the API server's configuration. Let's try this again. It's taking some time. Okay, should come back anytime. All right, so we're able to get pods. Kubernetes API server is up. So what are we doing here? We're creating something called a second secret, right? Look at that, second secret. And it's called my new key and my new value. Any new secrets created should be encrypted within the etcd data store, right? Before I get into the etcd data store, let me try and get this secret, my second secret, in YAML format. Okay, it's present inside the namespace called lab. So there is our secret, and that's our value. If I try to base64 decode this, there is the my new value, right? So when you want to access the secret legitimately, legally for that matter, the secrets are decrypted for you. Great. The only thing that's pending now is going inside. Again, let me copy this command back to my editor, see what this is. So we're executing a command inside the etcd pod using the etcd cuddle command. And we're trying to get the second secret value. That's what we're trying to do. So I'm going to copy and paste the second secret value here. And this time, even though the output is similar, you have these AES EBC, which indicates encryption, and there are no plain text values here. On the contrary, if I try to get the value of the secret that existed before, that's the my first secret. This was the first secret that we created. So this is the value of the my first secret, and it is not encrypted because we did not have the encryption configuration at that time before, right? We didn't have the encryption configuration before. So after we created the encryption configuration, any secret that we created gets encrypted for you. So if an attacker gets a hold of the Kubernetes etcd data store or the files that was used by the etcd data store, they don't have a lot of value now because they have to work on decrypting the secrets because they're encrypted, right? So that's how the encryption configuration behaves. In order to decrypt secrets at runtime, all you have to do is use the kubectl get secret option, and that's going to decrypt the secrets for you, right? So we created this encryption configuration manifest files, and if you want to encrypt Kubernetes objects other than secrets, all you have to do is mention them right there: secrets, config maps, any other custom Kubernetes objects that you create. You can also have multiple keys. You can also have multiple encryption providers. So during decryption, if you have a secret rotation in place, uh, each of those keys will be tried during decryption, right? And we've also seen this, how to get inside the etcd data store. That's the one large command that we executed in the lab, the one I tried to split down in my text editor, right? We actually did this. And we also completed this lab called Encrypting Kubernetes Secret Object at Rest, right? Now, I have a question for you, right? And that question is, we created an encryption configuration, right? When we prepared the API server, we created that encryption configuration. We pointed our API server to that encryption configuration, and then our secrets got encrypted for us. But if you look at this, the master key to encrypt and decrypt secrets is present in a file, and that file lies in plain text inside the API server, right? Now, in the context of Kubernetes, API servers are servers that only administrators should have access to. Such is also the case with etcd database. Etcd database is also a place only the ground administrators should have access to. But as with anything, with security, we have to worry about things that can go wrong. And what if somebody has access to the etcd data store? Well, we've defended that with encryption configuration. Now we have a new problem. The encryption configuration has a plain text secret, right? And that secret is present in plain text in the API server's file system. So you create a master key, and the master key lies in plain text in the cluster itself. So that's the example of the key that was used for encryption and decryption. Now, luckily, the Kubernetes development team has addressed this right from the get-go. If you don't want, of course, you don't want to have plain text secrets like this anywhere in your file system, unless absolutely necessary. So in order to solve this problem, the Kubernetes development team has created something called key management system, right? So this is the same manifest file, right? It has the kind called encryption configuration, the resources secrets, and it has a bunch of providers. So what we're going to see next is the same encryption file, a different type of provider. Previously, the provider was AES-CBC, and now we're saying the provider is a key management system called Vault. And the Vault here specifically refers to the HashiCorp's secret management solution, Vault, the HashiCorp Vault, right? This is what the solution is referring to. So you can offload your encryption and decryption secrets to an external secret management system, so it doesn't lie in plain text within your Kubernetes cluster. Right? You do that with this exact same configuration. Of course, there are other configurations. We do have a demo, but unfortunately, we don't have the time to go through that demo in this session. But it's available. It's fairly easy to get started. The only limiting factor here is you're going to have an external secret management system in the first place. Not just Vault. You also have other secret management providers like Azure Key Vault, right? The Azure KMS. And if you ask, is there one for AWS secret management solution? Is there one for GCP? Yes, of course, they're there. So in many secret management solutions that support securing secrets stored within the Kubernetes cluster, they support 4 providers. The cloud providers, Azure, AWS, GCP, and a non-cloud provider, HashiCorp Vault, which is an in-house solution that you can use, right? So when secrets get encrypted, remember, secrets only get encrypted when you create them, right? We saw before that the secrets that got created before were not encrypted at all. They were in plain text, right? My first secret was still in plain text, but my second secret was encrypted because my second secret was created after we created the encryption configuration. So if you created the encryption configuration using an external key management provider, how can you ensure all the secrets in your clusters are encrypted, including the ones that you're going to create in the future and including the ones that are created before? Well, you do that simply by reading all the secrets and creating them again. And there's the reading all the secrets using the Kubernetes kubectl get secrets command, and then you're recreating them using the kubectl replace command, which will ensure read all the secrets, create them again. And we know what happens when secrets are created after the encryption configuration. Well, they get encrypted. How do you decrypt data, right? There's a very simple way to decrypt data. You go to the encryption configuration you created, and then under the providers section, you make identity as the first option. And when you do that, secrets get decrypted from the etcd data store. If at all you decide that you don't want etcd encryption anymore, that's something that you could do, right? And remember, I mentioned about a role-based access control for secrets. There's an OWASP top 10 list for Kubernetes risks. One of those risks is overly permissive RBAC configuration. It applies to many Kubernetes objects in general, but it's also applicable to secrets, right? So imagine you have a pod, right? And that pod is going to have a cluster admin role on the API server for whatever reason. That's something that's questionable. And if another pod has permissions to list secrets, not read secrets, but to list secrets, listing operation in Kubernetes lists not only the names of the objects, but also the details of the objects. And if you're able to get the details of an object called secret, that would be you being able to read the plain text secrets as well. So generally, if you want to read an object, you want to read the details of an object. But if you want to list all the objects, you just want to list the objects, their names probably, not their details, right? That's general expectation. But here, if you're listing Kubernetes objects, you get the details, name of the objects, and the details as well. If the object that you're trying to list is secrets, you not only get the name of the secrets, but you also get the details of the secrets as well. So when you're configuring RBAC, if you're configuring role-based access controls for secrets, remember that list permission on secret is as powerful as the get permission on secrets. Okay? So this is the slide that we started with before, or we have dealt with direct access to the etcd database. If someone has direct access to the etcd database, that's something that we can fix with encryption configuration, right? Executable files, secrets present in image layers. You have secret scanning solutions that you can scan during your development workflows, try to find those secrets, and then validate those secrets by creating new ones, by rotating those secrets, right? So Kubernetes secrets objects. If you don't want to store secrets within your executable files, you can use the Kubernetes secret objects to store those secrets. And if you don't want to store secrets in container layers, you can also use the Kubernetes secrets object, right? And we know how to secure Kubernetes secrets object to a reasonable degree by using encryption configuration with an external key management solution to encrypt data, right? What are the two ways to create Kubernetes secrets? Well, one is a kubectl command. Two, using the Kubernetes manifest file with the kind secret, right? These are the two ways to create secrets in Kubernetes. And we've seen this before. Leakers in Kubernetes, hey, executable files, you don't want secrets in your executables. Maybe you want to use Kubernetes secrets instead. Container layers, you don't want to put secrets in your container layers. You want to use Kubernetes secrets instead. And when you're using Kubernetes secrets, you make sure you have encryption configuration and you use an external key management solution to store the encryption and decryption key. That can be HashiCorp Vault or one of the secret management solutions from the big three cloud providers. We still have to address the problem of if people create secrets using manifest files, they'll have to be stored into the version control system, right? They'll have to be stored into the version control system. And how do we protect secrets in version control systems? This is not very new. Protecting credentials in version control systems, there have been many solutions. In fact, we've had 2 decades of good secret management practices when it comes to not storing secrets into version control systems because we know it's very, very bad. But in the context of Kubernetes manifest files, there are at least two solutions that exist that are worth trying out. So let's first see how secrets are created in the version control system, right? So here we have a Kubernetes cluster. It has encryption configuration. So everything in the etcd data store gets encrypted. Great. And now here's our version control system, which has those secrets in base64 encoded format, right? Another secret in base64 encoded format. They're encrypted in etcd data store, which is great. But in the version control system, they're not encrypted. How do we protect these secrets in version control systems? All right, so there's a secret in version control systems. There's a special third-party tool from a company called Bitnami, who produces many great open source software. That's called Field Secrets. So what you do is in your developer workstation, before you check in your manifest file containing secrets, you use a command line interface called kubectl to seal the secret. That is to encrypt the secret, which is then safe to be stored within the version control system. And from the version control system, when your CI/CD system is reading that manifest file and deploying it to the Kubernetes cluster, the Kubernetes cluster recognizes, oh, this is not a regular secret. This is a secret that is created by the kubectl command. So I have to decrypt it first and then give it to the etcd data store, right? So these are two components of sealed secrets. So we're going to see a pictorial workflow of how this looks like. Of course, you're going to have to install the sealed secrets binaries, both within the Kubernetes cluster and into your developer's workstation. And you have to distribute keys. There are, sealed secret supports different types of keys, and it also supports rotations. It's a great tool. So here's your developer's workstation. Secrets are unencrypted, base64. And then you do kubectl, take this file and give me an encrypted manifest file, right? Look at the manifest file about. The kind is called secret. After going through kubectl, we're going to get a new object called sealed secret, right? Sealed secret. And then there's encrypted data. So when we create a Kubernetes secret object using this sealed secret file, the call is going to be intercepted by a special type of controller called sealed secrets controller. Kubernetes cluster has multiple controllers. In fact, there are 30 plus controllers that get shipped out of the box in many Kubernetes installations. So when you install the sealed secrets tool in your Kubernetes cluster, it also installs a special controller called sealed secrets controller that recognizes this is a sealed secret, and then it decrypts them, stores them in the etcd data store plain text. But you do know how to prevent this problem in the etcd data store. As long as you have the API server's encryption configuration, when sealed secrets actually creates a secret in the etcd data store, that gets decrypted for you. So now, if you look at this picture, you have a version control system where your secrets are encrypted as well, and your etcd data store, the secrets are encrypted as well, right? So this is one way to prevent leakage of plain text secrets in your version control system. Is sealed secrets the only solution available? No, there's also another solution available called Mozilla SOPS, Mozilla SOPS. We'll look at that later if it's part of the slides. So this is, again, a command line walkthrough of, here's a generic opaque type of Kubernetes object, how you install the kubectl command as the installation steps, and then using the kubectl command, I think there are further installation steps there. Okay. Reviewing encryption and decryption keys. Okay, so you're getting the so that's the kubectl get command, creates a special type of secret for you during installation, and that's what's actually going to be used for encryption and decryption when you're using sealed secrets. So that's the certificate file that gets created for you within the Kubernetes cluster when you use the kubectl command. Okay, so the kubectl command does not use a single key for encryption decryption. It uses a public-private key pair, and that's what you're looking at. During installation, this is automatically created for you. If you're in a single node cluster, this is going to be easy. But if you're in a multi-node cluster, you will have to make sure this key is available in all the etcd data store. And on the developer's workstation, the keys are available for encryption. That's also something that you need to make sure, right? So here are steps to distribute the public key to a developer's workstation. Okay. And then once the developer has the secrets, they're using the kubectl command to seal database.credentials file and create a new file called encrypted secret YAML. Okay, so what happens when you execute that command? When you execute that command, the database.credentials.yaml file, which has the base64 secrets, becomes a encrypted dash credentials.yaml file with encrypted data inside them. Okay, and now this file, is safe to be stored in the version control system with all your git add, commit, and push commands. During decryption, all you need to do is the kubectl apply command to apply this file, and that's it. The sealed secrets controller is going to intercept this call and it's going to create the secret for you on the fly. Okay, creating decrypted secrets when you're inside the Kubernetes cluster is as simple as using the kubectl git command and to decrypt those secrets, right? So far, we've seen two solutions. Number one, if you have secrets in the etcd data store, how to decrypt them, how to encrypt them using a special configuration value called encryption configuration. And then we looked at, okay, people store manifest files in version control systems, and it's not fair to have secrets in plain text in the version control systems. You'd want to encrypt them using Mozilla SOPs, which is a solution that we haven't seen, but the solution that we have seen in this presentation is called sealed secrets. That helps you keep your version control system safe. Sealed secrets is particularly meant for Kubernetes clusters. The other solution that I was talking about, Mozilla SOPs, is a general purpose file or data encryption. It's a general solution to encrypt data present within a file, right? Not specifically meant for Kubernetes, but also plays a good role in encrypting secrets with Kubernetes. But Mozilla SOPs is something that you can use for other solutions as well, apart from Kubernetes. Okay, so so far, we have been talking about putting secrets in Kubernetes, right? And we created those secrets using manifest files. But not a lot of projects behave this way, right? Let's quickly take a look at how encryption decryption behaves, like a quick recap, right? So here we have the etcd data store encrypted with encryption configuration. And we also have the version control system encrypted either by using sealed secrets or by using Mozilla SOPs, right? So there's the encryption configuration. This is what we've seen so far, right? And if you take a look at this, these two solutions there, sealed secrets and Mozilla SOPs, they also require external keys to be maintained. You can choose to get those keys from an external key management service or external key management services like HashiCorp Vault, Azure, or one of those providers. But in a lot of projects, if you are using an external key management provider, there are chances that your application secrets are already present inside those external key management provider. And if you have secrets present in an external key management provider, you don't want to recreate them manually using manifest files inside your Kubernetes cluster, right? If you want to bring them inside your Kubernetes cluster, if you want to bring external secrets inside your Kubernetes cluster, there's a special type of driver available called Secret Store CSI driver. And that Secret Store CSI driver fetches secrets from the external key managements, right? Let me play this animation for you. That external secret store fetches secrets from the external key management services and mounts them dynamically to the workloads that actually require them. It does not use the Kubernetes secret object at all, as you see in this picture. So Secret Store CSI drivers, by default, does not use the Kubernetes Secret Store CSI driver at all. If you want, you can configure the CSI driver to replicate all those external secrets or specific external secrets inside the Kubernetes secret object. You could do that if you want, absolutely. But if not, if you have a Python PHP application or a Go Node application running inside a pod that wants to authenticate to a database or a caching store, you could directly use this workflow here. If your secrets are in the external key management store somewhere else, use the Secret Store CSI driver, bring those external secrets, mount them directly to the workloads that require them as a volume mount. Right? So this is very helpful. Secret Store CSI drivers is very helpful. In fact, when people start implementing Kubernetes, at least a couple of years before, people started consuming secret objects, but later realized that it's only base 64 when security teams intervened. And then Secret Store CSI drivers was in beta phases before. And now we have other solutions as well. Similar to Secret Store CSI drivers, there's also one more solution called ESO, which expands as External Secrets Operator, which also brings secrets from external key management store inside your Kubernetes cluster in a little bit of a different fashion compared to the Secret Store CSI driver. But those are two solutions you can use if you have secrets present externally already, and if you don't want to bother about the Kubernetes secrets itself, Kubernetes secret object itself, right? So the supported providers by the Secret Store CSI drivers are the AWS, Azure, GCP, and the HashiCorp Vault, right? Let's quickly look at an example of how this works, right? So with Secret Store CSI driver, you create a special kind called secret provider class. And in that secret provider class, you provide the key vault name in Azure. And then within that key vault, what are the particular type of objects that you want? And then in Azure, it's the tenant ID that you want to supply. And then from within the pod, you specify a volume that's based on the Secret Store CSI driver, right? So there's a driver that fetches secrets externally, fetches secrets from external places, and this is a way you can bring them inside the pod at runtime, right? Also, let's quickly look at how to do the same thing with HashiCorp Vault. There's a secret provider class. The metadata, we're going to give it a name, Vault. And then we specify the provider as Vault. Previously, the provider was Azure KMS. And now we supply parameters. In Vault, you specify the Vault API address and the role name. Roles are very specific in Vault. Then you specify the objects and the path where those objects are stored, right? And then you do the same thing. Bring them inside a volume where the pod that requires that secret can actually use that secret to authenticate against other systems. Okay, and if you want to execute those, you can execute and test this. Okay, so here we have the Secret Store storage driver. Bringing our external secrets, mounting them as volumes inside the pod. So what have we managed so far with respect to secret leakage? With respect to version control systems, we know that we can use sealed secrets, Mozilla stops, or an external key management solution. With respect to secrets present in configuration files. We can use Mozilla Softs as a general purpose encryption tool, or we can put our secrets on an external KMS. With respect to executables inside containers having secrets, we can consolidate them as Kubernetes secrets, or just grab those secrets externally through secret store CSI drivers. Container layers, we can do the same thing. With someone having direct access to the etcd data store, there's also encryption at rest that can be enabled at etcd using something called encryption configuration that we saw in the demo. And when you're using encryption configuration, you would want to store the encryption decryption key in an external key management solution, right? You may choose not to use the Kubernetes secrets object at all, but then there are some tight integrations. If you have a pod that has a container image, and that container image is present in an internal registry requiring a username and password, registry credentials, to authenticate and pull an image and then create a container and a pod out of it, then you would want Kubernetes API server to know that username and password to authenticate with the external registry. And to do this automatically, there's a special type of Kubernetes secret object called registry credentials. And those are some tight integrations present within the Kubernetes API server and the Kubernetes cluster itself. So while you may choose not to use Kubernetes secret object for 90% of your workloads, if you have secrets externally, you can bring them with secret store CSI drivers. For some operations, you would still want to rely on the Kubernetes secret object. And when you do, make sure that they're stored properly, securely in version control system, and make sure those secrets are encrypted at rest using encryption configuration of the etcd data store. So that's quickly an overview of how we can address these different secret leaks using the number of different options for secret management and secret encryption available within Kubernetes. I want to show you one last thing, and that is secrets in environment variables versus secrets in volume bounds, right? So how do you consume secrets from within a pod? There are two primary ways. Number one, how people choose to use environment variables. There's nothing implicitly wrong in it, but we're going to see shortcomings of what can happen when something goes bad and where environment variables get leaked, as opposed to storing something in a volume mount. So imagine you have a Kubernetes secret object called mySecret. And if you want this secret to be available as an environment variable inside a pod, then that's the pod manifest that you will create, the env, and the value of the env is supposed to come from a secret. Okay? So this is going to make the my-secret available as an environment variable inside the pod. So if someone has access to the pod inside, they can use the env command or the print env command to look at the secret. Similarly, if you want to mount a Kubernetes secret as an environment, this is the same thing. This is just mounting multiple secrets in the same pod. Well, the problem with environment variables is when a program crashes, environment variables are written to the crash logs. That's not all. If you use commands like docker inspect or crictl inspect, environment variables are populated within the output of that command, which is what is used by multiple container runtime monitoring tools. So if you have secrets in them, they also get to your monitoring tools somehow. And that's exactly why secrets and environment variables is kind of a questionable security practice. Is there a better alternative? Well, the only better alternative is mounting secrets as volume mounts inside a pod. Of course, this doesn't prevent all the scenarios. If an attacker gains access, a shell access inside a pod, just like how they can use env or print env to display environment variables, they can enumerate through your file system and grab these secrets as well. And of course, you can control this to a certain extent using ACLs, access control lists, and files and directory permissions, but it still gets exposed. But if you have secrets inside volumes, they don't get written to program crash logs by default. They don't get displayed as a part of the Docker inspect command, and they don't get displayed in the container runtime monitoring tools as well. Okay, that's why it's preferable to have secrets in volume mounts in comparison to environment variables. Okay, so that's where I want to leave you with. This is pretty much the end of my presentation. N different ways to mount. There's one more slide saying how you can mount multiple secrets, that's volume mounts, from within your pods. Okay, so different ways to manage Kubernetes clusters. Some of the solutions that we saw, encryption configuration is a solution that we saw. And then we looked at how to store encryption keys in an external key management solution. Then we looked at, hey, people are going to create secrets in manifest files, and they're going to put them in version control systems, and how you can protect them using sealed secrets or Mozilla SOPS. And then we looked at a case where people have secrets in external key management solutions. Why recreate them within Kubernetes unnecessarily? Why can't we just bring those secrets to our workloads? Well, you could do that with the secret store CSI drivers. There's also one more solution that does the same thing in a little bit of a different fashion. Brings external secrets from within your Kubernetes cluster, and that's ESO, External Secrets Operator. Those are some options that you have to manage secrets efficiently within the Kubernetes cluster. So DevSecOps Live, hosted by Practical DevSecOps, where we bring in external speakers, subject matter experts to speak on anything related to DevSecOps, cloud security, containers, Kubernetes security, and LLM security as well. Stay tuned to our LinkedIn page where we post these events, and I'll see you on the next one. Thank you very much for your attention today. Bye-bye.